Uh, Good morning, everybody. Great to see you. I'm Tracy Sprower with Methow at Home, and this is one of our programs with our beloved resident naturalist here in the Methow Valley, Dana Visalli. We're going to be going deep into the seeds of the beginning of life that we find here today. I'll let you introduce yourself a little bit more. Yeah, that might not be entirely correct. Seeds or spores. Anyway, Dana, I'm going to pass it off to you, and thanks for being here.
Yeah, thanks to people for coming. I forget how this arose. I did give this talk about 10 days ago in Tonasket, and I called it The Evolutionary Journey of the Flora of the Okanagan. And now it's the evolutionary journey of the flora of the Methow, because they're the same plants and it's the same journey. So what I don't spend my time thinking about this. You might think I do, but I don't. It's more like what needs done in the garden before it snows, and what do I need at Hank's, and the mundane aspects of life. And meanwhile, we are embedded on this planet with this massive evolutionary journey. And so when I give a talk like this, my mind gets to go in that direction and think about those things. And I find it invigorating, actually. It's nice. It's always nice to get out of the self, don't you think? and into the larger story. So should I hit share screen?
You bet.
Working on it here. Hit it, nothing happened. There we go. So that probably came up.
Yes, indeed. And then you just go to your slideshow so
Right.
that we just see the slide.
Hey, that happened. That happened when we practiced this yesterday. I don't know why that happens. I'm going to try that again. Alt S. Okay, I can do this another way. I'm hitting Alt SS. That should bring, but there's something. So we do have a slight problem here, and that is that the menu up on the top of the page is in the way. View. Maybe it's in view. Slideshow. So you guys.
Ta-da! Excellent. Yes.
Okay. Well, this is a bit of.
Okay. Just a reminder before we start, Dana, if folks could go ahead and mute yourselves, if you're just check to see if you're muted, that would be great. And for those who are just now joining us, Dana has generously said, if you have a question, go ahead and just unmute and ask your question, or you could raise your hand or put it in the chat. Okay, thanks.
Thanks, Tracy. So I think this program is both somewhat complicated compared to what we spend most of our time thinking about, and also not totally complicated. I mean, towards the end, I even go into, because we talk a little bit about photosynthesis, I show a picture of a hydrogen atom. And I think as soon as you see a picture of a hydrogen atom, you start to your eyes start to gloss over, because none of us really, most of us don't get chemistry. But the actual information, most of it, I find I can understand. I can understand the basics. I mean, I'm rereading A Brief History of Nearly Everything for at least the third time. I don't get very far at night when I go to bed, but I do love that book. And I got to a section on atomic structure last night, and I forget which of the physicists was. It said, don't try to understand atoms, and don't try to understand how these atoms work. So all we have are models of how. This is not about atoms, this program, but if you're going to talk about photosynthesis, you have to know something about the connectivity that exists at the atomic level. So there are some mild complications, and actually, to close in on this picture, this is called steer's head. And and there are complications with this too. Everything in life has a certain level of complexity. So this is a flower that grows in the Methow Valley. It's called steer's head for obvious reasons. It's hard to find. It's not common. It's not totally uncommon. I usually find it under bitterbrush. It only grows about 3 inches high. But obviously it's very charming. It's only present in the spring, depending on your spring depends on your elevation. I have found it up on I forget the name of the butte up there, but like near Sandy Butte in June, because the flowers are just blooming there in June. But in the valley floor, I would say late April, early May, and if you go mid-May, it's already dried up. So that's one of the reasons it's hard to find. It only gets a couple inches high. A great plant. So it has evolved this shape for a reason. What could possibly be the reason? Well, the reason is reproduction and successful reproduction. And a flower that has this kind of a complex shape limits what pollinator can get at it. And what that does is it ensures that the pollinator is a skilled pollinator. We're talking about bumblebees, a skilled pollinator that will go to another steer's head and deliver the pollen. Other flowers are just generalists and they don't care who pollinates it. And it's a very curious thing about life on the planet is many things work. Many things work. I mean, I think about that for myself with, with our own species and how all these different ways there are of trying to live on the planet. And some of them seem so strange. And it's like, sorry, many things work. There are many ways to be alive on the planet. So some of the complexities of this flower, it's got to offer something to the pollinator, in this case, a bumblebee. It has nectar up in those horns. So the bumblebee will land on the flower and stick its proboscis, its nose, in one of those two holes that look like eyes, and it can reach the nectar. And in the process, what looks like a snout splits open. You can see there's a line down the middle. It splits open, and the anthers spring out, and they hit the bumblebee on the belly, which is a hairy belly with little barbs to catch pollen. The flower is delivering pollen right to the belly of the bee, and the bee gets a little reward and goes. And then because bumblebees tend to work one species at a time, it goes to another steer's head and delivers that pollen. Well, that's a long evolutionary journey to assure reproduction. And I find of course, we take reproduction for granted, but the reason everything has to reproduce is because life on the planet is dangerous. Nothing lives that long. Bristlecone pines live 5,000 years, but they don't move. They stand in one place. For 5,000 years, they have 4 inches of bark to protect them from the vagaries of life. So life is kind of a compromise on the planet with the adversity, both of the cosmos, cosmic radiation, and the challenges of being alive on the planet. So this plant, what else? Let's see. It offers that reward. It's also poisonous. To keep herbivore predators from eating it. But there is one herbivore that has adapted to that, and that is this Clodius parnassan butterfly. I just pulled the picture of that up. And it is able to isolate the toxins in the plant in its own body so that the caterpillar and the butterfly are toxic to predators. That's why Clodius parnassan has red dots on it to warn predatory, mostly birds, that it's toxic and don't eat it. So this relationship has developed between the animal world and the plant world. So all this complexity on this flower that is so charming, but almost impossible to find in the Methow because it's so small. Look for it in late April. So that's the nature of life on the planet. It's complex and full of long stories. We're talking about the flora of the Methow. Flora doesn't actually, the word flora means flower, but when you talk about flora, you're actually talking about all the plant life in a given location for the Methow. Like the book for the plants of Washington State is called The Flora of the Pacific Northwest. It's a big book. Botanists love it. But it's not just flowers. It's all the plants in the Pacific Northwest. So that's what we're talking about briefly here, are various plants. So here is a collection of plant and plant-like organisms. So that first thing on the upper left is an algae, a green algae. It's a desmid, a single-celled green algae. Well, green algae is now often included in the plant kingdom. It used to be in a different kingdom, Protus, and we'll talk a little more about that. So anyhow, there's all this variety. We can't linger any too long on any one slide, but we recognize the rose, obviously a flowering plant. The upper left is a very strange plant called Welwitschia that only grows in the desert in Namibia and is actually a gymnosperm, which means it's not a flowering plant, and it does mean that it's related to conifers. Doesn't look like a conifer to me. Well, not quite a conifer, but it's in the same group as conifers, gymnosperm. And it has some interesting tricks that it does. It's wind pollinated, but it puts out this little fluid to catch the pollen as it blows in the wind, and the fluid has a little sugar in it, and so insects start coming. And it's considered to be possibly a step in the journey from wind pollination to insect pollination. Drosera, sundew, that the second plant, second row, I'm not going to name all these, but the second row on the left is sundew. It's a carnivorous plant. It eats insects. And while we don't have it in the Methow, there's a lot of it in Swamp Creek. If you remember driving the North Cross State Highway and you go over Rainy Pass and down the other side, pretty soon you cross a sign, you cross Swamp Creek. It starts at Snowy Lakes. So we have these carnivorous plants close to the Methow. Actually, we do have one species in the Methow, Pinguicula butterwort. Anyhow, just the variety of plants. On the third row on the left, worthy of mention, that's a ginkgo. Many of you would recognize it. So these different plant divisions have a various number of species. The rose at the top is in the division of flowering plants, and there are 300,000 species of flowering plants on the planet. We call that success. Ginkgo, guess how many ginkgo species there are on the planet? One. There's one ginkgo. And right next to the ginkgo is a willow catkin, a male reproductive structure. And I bring it up because botanists love willow catkins. And from there, lots of other variety in that we're not going to name them all. These are all efforts to reproduce. Why don't things live forever? Because they can't. Life is too tenuous. Life has a toehold on the planet and has to reproduce regularly and get young again.
Hey, Dana, we have one question that has come in here. Going back to the steer's head and the butterfly. Does the caterpillar of the butterfly eat the steer head plant itself, or the butterfly drink the plant nectar like the bumblebee, or both?
Yeah, good question. No, the caterpillar lives on the plant. It eats the leaves. In fact, I remember some years ago when our butterfly man Robert Michael Pyle came to the valley, and we knew we had this butterfly, but we didn't know we had steer's head because it's hard to find. And we knew that this butterfly only lived on that family. Sorry, I cannot remember what family this is in at the moment. Same family as bleeding heart on the west side. And we knew that some species of that family had to be here. And then now we can find this plant because we know where it grows, but it's hard to find. So it eats the plant and absorbs the toxins from the plant and becomes toxic itself. So the caterpillar's toxic and the butterfly's toxic. But it obviously doesn't kill the butterfly. So the tree of life, I always actually enjoy seeing this. And there are currently a lot of this material's arguably arbitrary. So I'm going to say there are, I think, 6 kingdoms of life. I don't know if I circled them all. There used to be 3. when we went to school, there were 3. Now there's 6. There could be 7. It's a little arbitrary. We're just trying to understand the evolutionary journey, especially the taxonomists are trying. So we know there's animals, fungi, plants, algae. I think I circled here first that word at the top, eukaryotes, and then prokaryotes. I circled those 2 words because that is the first major division in the tree of life, the family of life. In fact, I don't know when it comes up here, not right away, but at the very bottom, it says last universal common ancestor, abbreviated as LUCA. It appears.
Take your
It
time.
appears that
I'm just wanted to hear this talk.
Sue, you need to mute yourself. Thanks. Last universal common ancestor. All this diversity. There's 300,000 species of flowering plants. There's probably 400,000 species of plants. There's 1 million insects. I forget how many total species we may now think they are. All this diversity started out as one organism, one time. It appears that life only appeared once, and all living organisms are related to LUCA. So I circled over on the right there, the algae and the single-celled eukaryotes. Algae is sometimes put in with other single-celled organisms, or I should say single-celled organisms. And now green algae is often included with the plant kingdom. It's squishy where they go. So these are eukaryotes and prokaryotes. I mentioned those 2 words, and it is the first major division of the tree of life of all living organisms. You are either a prokaryote or a eukaryote. You'll have to decide for yourself which way you're going to go. But prokaryotes are much smaller cells and much simpler cells, far less complexity. And so that's a measurement there. And I had that measurement's a micrometer. 1 micrometer is a millionth of a meter, utterly invisible. Human perception starts at about 200 micrometers. So we can't even see eukaryotic cells, which go up to 100 micrometers. You can see it in this artist representation that our cells are all eukaryotic cells. We are eukaryotic organisms. That's the animal kingdom. Same with the plant kingdom. Bacteria are prokaryotic, far simpler. Prokaryotic cells don't have what they call organelles, small little organs inside of the cell. You can see in the eukaryotic cell, those things that are sort of turquoise blue, or I think are probably mitochondria. It's an organelle. It's membrane bound. It actually has its own DNA. As you remember, mitochondrial DNA. It reproduces on its own, independent of the reproduction of the cell. Well, I don't think there are mitochondria inside prokaryotic cells. So I'm just saying there's this big division. You can look into it further if you want. So how did life complexify? Life started out as one simple prokaryotic cell. Apparently, after all these years of deep scientific insight, I would say we have no idea how life arose. But we do know that once it arose, it has ramified and complexified. Well, one way that life has complexified is through symbiotic union. Symbiotic means life together. It appears, it's widely agreed, that certain cells that engulf and eat other cells at some point was unable to digest the cell it ate, and they began to work together. And that is true for chloroplasts, which are organelles that perform photosynthesis. They turn the light coming from a star 93 million miles away into stored energy, sugar. They started out as their own independent organisms, a bacterial cell, cyanobacteria. It was engulfed by a eukaryotic cell and became part of the cell. I mean, you could almost find hope for the human condition in the fact that everything eats everything else, life also works together in major, major ways. So we're talking about the flora of anywhere, but in this case, the flora of the Methow. Here's the plant kingdom. So you can't remember all this stuff. So for now, it's just interesting to remember, to review that all these different kinds of photosynthetic organisms exist. And what are the numbers? Well, the numbers are here. So chlorophyte at the top. Chloro means green. I think you can probably see my cursor. I'm circling chlorophyte. Chlorophyte means green. Phyta means plant. Green plant. Green algae, they're sometimes included in the plant kingdom and sometimes not. Fortunately, we don't have to make that decision. In this chart I probably got from Wikipedia, they're in there. How many green algae are they? Well, there's about 4,000 species known of green algae. They're so small, they're hard to identify. There's probably more than that. We don't have to name all these, but we'll talk a little more about several of these because charophytes are interesting. That's the second one. So chloro means green. Char, I kept looking it up, and it actually means, it's like Latin for unknown plant. Some of these, it helps remember the word, but it's also can be amusing. So charophyte means unknown plant. It's a type of algae. It's photosynthetic, and I have a picture of it coming up. And I emphasize it because these stoneworts are a common name for charophytes. We have a lot of stoneworts, not a number of species, but a lot of bulk of stoneworts, and you probably don't know what they are. There are that many species. So some other organisms in the plant kingdom. Liverworts, we've heard of them, might be able to identify them. Hornworts. I've never seen a hornwort. Never seen a hornwort in the Methow, nor anywhere else. Mosses, club mosses. We've heard of these things. Ferns. Let's see. How's this work? Yeah. Look at this. This is up to date. Horsetails used to be in their own division and are now considered a fern. They're in with the ferns. All these words mean something over here. They're in this division. Pterophyta. Well, pterido means feather. These are feather plants. Well, why would they call ferns feather plants? Because the leaves look like feathers. I mean, it helps, when you break down the Greek or Latin meaning, it can help deepen your understanding of the word and even remember it. Cycadophyta. Not very many cycads. Ginkgophyta. Look how many ginkgos there are in the world. One. It's really a relic species. Pines, conifers, etc. Gynophyta, we don't know what gynophytas are. I do talk about them. So down at the bottom are the flowering plants, and they use the name Magnoliophyta, and I don't know why, but it's also called Anthophyta, and it's called Angiospermophyta. I'm just pointing out a lot of this taxonomy is not 100% agreed upon or settled. And number of flowering plants in this graphic, which is probably 10 years old, it says 250,000 species. So I updated it to 300,000 because this is a work in process, trying to figure out what organisms live on the planet are accompanying us through space is no small trick. And it's to the credit of humanity that we take this much interest in the world around us. So this looks complicated. It's got some interesting stuff. These are the same divisions that we just looked at. Stoneworts, remember the Charophyta and Chlorophyta, that for some reason I put them together here. I put this thing together myself. Liverworts, hornworts, mosses. Well, let's see. I think I have some circles here there's something going on here. There's more X's at the bottom of this chart than there are at the top. And really what I'm trying to illustrate here is there's change over time. Life changes over time, and it complexifies over time. And arguably, more X's means more complexity. And what do the X's mean? Well, you can look at the top. So in this first row here, this is the male reproductive cell for these organisms. How do liverworts reproduce? They have a flagellated male gamete, basically a sperm that has to swim. That means it needs water. Life first evolved in water. Plants probably first evolved in water. They definitely did. So they could afford to have a male reproductive gamete that swam through water. How are you going to colonize land? You're going to have to get rid of that tailed gamete. And they did. Cycads, none of these have a tailed gamete. There's a shift here. A lot of this is about colonizing land. Look at this, a vascular system. That means you can transport water through your body. Well, the first organisms don't have stoneworts, liverworts, hornworts, no vascular system. They don't get more than an inch high because they can't pump water or move water upwards, but the other organisms can. Pollen, how are you going to colonize dry land if you reproduce with a sperm that has to swim through water? You can't. So over time, life evolved this strategy to cast the male, still we'll call it male, nothing overly male about pollen, cast it to the wind or have an insect carry it. Seeds, lignin, which is wood, which means you can grow upright. So these early plants, they don't grow more than an inch tall. The tallest plant in the world is a redwood tree in California. It's 400 feet tall. It's wood that made that possible. And what's the advantage of wood? I'm afraid it's competition with the other plants because they're all trying to reach to the sun. They're competing for sunlight. Well, redwood trees are the evolutionary winners of that battle. Flowers, how many of these organisms have flowers? Only flowering plants. What's the advantage of flowers? The primary advantage is attracting an organism from another kingdom, known as an insect, to come pick up your pollen instead of blowing it to the wind. And we talk about that, and we're going too slow here. Okay, there was that major division in the tree of life, prokaryotes and eukaryotes. There's a major division in plants, monocot or dicot. What does this have to do with the flora of the Methow? It's totally true in the Methow. All the plants in the Methow, all the flowering plants are either monocots or dicots. So what is a monocot and a dicot? Well, it's two very different evolutionary lines that probably converged, which means they didn't split. That's my reference when I say that. They're probably flowers, I think, evolved twice. Monocots and dicots are so different that I don't think one evolved into the other. It just is it's a strategy for reproduction that works, so it evolved twice. What's some of the differences? Well, up here we have leaf veination. Monocots have parallel veins. I think I pull up over here. So lilies, orchids, and grasses are monocots. Well, if you think of a grass, this sort of looks like a grass leaf, a fat grass leaf. If you look at a grass leaf, all the veins, they look like railroad tracks. They're parallel. That is one of the characteristics of the monocot group. Another characteristic is the flower parts are in threes. So here's a flower. It has 3 stamens and 3 petals. Now, it might have 6 petals, or it might have 9 petals, but they're in groups of 3s. That's all. It can only count to 3. Dicots, different. Dicots have net veined leaves. Maple leaf or sycamore is a classic example. The veins radiate outwards. They're not parallel. Flower parts are in groups of 4 or 5, 4 or 5. So it might have 4 sepals. This has 5. It might have 4 petals. This plant, 5 is a more common number, or it might have multiples of 4 or 5. Major different strategy. The larger difference is really in the physiological structure of the plant. They have different, the way that they form their seeds is different. Down here, I think we don't need to really try and explain what that is. And the arrangement of the vascular system is very different in monocots, where it's spread throughout the stem, and organized differently in dicots. So we're just pointing out, if you're going to try and identify a plant, the first thing you need to figure out is if it's a flowering plant, a monocot or a dicot. So here's a few dicots over there in the upper right. Composites, that's the aster family. The aster family is the largest family of flowering plants on the planet. There are about 25,000 species of flowering plants, of composites of aster family plants. That's all includes, you could call it the sunflower family, used to be called that. It's now called the aster family because the scientific name is the Asteraceae. So it's now called the aster family. Well, the second largest family of plants are orchids with 20,000 species. So as usual, various strategies for survival and reproduction work. Pea family is very large. I forget exactly at the moment species. But grasses, which have 12,000 species on the planet, grasses cover 30% of the Earth's land surface. How successful is that? So many things work, and life tries everything, and some things don't work. Many things go extinct. Well, there were no plants There were no plants on the surface of the earth for a long time. I have a picture that comes up, and I think it's like the first land plants were probably, not remember at the moment, but maybe 500 million years ago. The planet is 4.75 billion years. So for much of the history of life on Earth, there were no plants on land. Well, plants capture the energy of the sun. They make food. How many animals do you think there were on land before there were plants? And the answer is none. There was nothing. There was no food. There was no energy. Plants make all the energy. Some of you have seen this before. It's a picture I took of the Methow 18,000 years ago. This is Silver Star during the last ice age, 18,000 years ago. And Gardner, I'm kidding. I'm not actually 18,000 years old, but so the point here actually is life not only had to colonize land, but it got pushed off the land and had to recolonize the land. There were no plants in the Methow 18,000 years ago. It was a massive ice. There might have been a few plants on the summits of these peaks, but it was not a hospitable environment. So this didn't happen just once. It happened 20 times. There were 20 glacial advances in the last 2 million years. So life is very dynamic over time. The story of the ice ages and the relationship of life to the ice ages is interesting enough that people have written books about it. This is my favorite book on that subject after the ice age, written by a Canadian ecologist. She's got interesting graphics like this one in the book. So these are, I don't know how well you can see it. You can probably see it fairly well. This is a maple seed, double seed, and a chestnut, which of course is a seed, and white pine. Well, all these species now exist in northeastern the United States. They all exist together here. But during the Ice Age, these species were pushed further south. This was their refugia during the last Ice Age, and this was the refugia of white pine and hemlock in the last Ice Age. Well, they had to move. These plants had to travel. Plants can't walk. How did they manage to move? They each have their own way. You can see maple has wings. This breaks apart, but you've probably seen how a lot of our pines have these wings, and they flutter down from the tree, but they don't come straight down. They flutter out to the side of the tree. So over time, they're able to move. Well, how does a chestnut move? It probably weighs, I don't know, like a quarter of a pound. Squirrels carry it, and then they bury it. So this is in a symbiotic relationship with mammals, but that's how it got back after the Ice Age. So these different divisions, we're going to go through them briefly. We looked at this in a different context earlier, the plant divisions of the plant kingdom or of the Methow. So how many, I have the charophytes and the chlorophytes together here, green algae and stoneworts. And I'm going to talk a little more about stoneworts because I think the name's a little mystifying. How many in the Methow? Nobody knows. They reproduce with a flagellated gamete. Why? They're aquatic. They live in water. They can afford to do that. These are chloroplasts inside of this green algae called volvox. Well, chloroplasts evolved in bacteria. And the only reason they exist in plants is because of endosymbiosis. I talked briefly about that. They somehow got incorporated into the body of larger organisms. They first evolved in bacteria. Really, the early stage of life is bacteria. And we have more bacterial cells in our body than we have human cells, interestingly enough. Here's a little picture of endosymbiosis. This larger organism is trying to eat this creature, but it fails to digest it, and they begin to work together, which means there's hope for humanity. So here are some stoneworts, and I put this in because I'm so impressed with these stoneworts because they're so common in our lakes. We used to go to Buck Lake for the 6th grade camp out, and I would put these milk jugs on a rope floating in the water, and the kids would have to canoe out and go around the milk jug and come back to shore. And then I would pull up the milk jug, which was held in place with a rock, and it would just be coated, completely coated with this stinky stonewort called chara, which I definitely, I defined that it means unknown plant in Latin, unknown plant. So the point is we have these organisms. Well, chara is now thought to be in the evolutionary line to land plants. You can see it looks like horsetail. Looks like a horsetail. It's not a horsetail. It can only live in water, but it has various affinities with certain land plants, including the same kind of chlorophyll. So it's an evolutionary journey. If we were to age these would be these would have we could find fossil evidence of these long before we can find fossil evidence of flowering plants. I put the desmond in. The desmond is also it's in this division Charophyta. I don't know why, but I put it in because of the symmetry, the striking symmetry of most of the desmonds, as far as I know. It's almost a green algae. It's a charophyte, which is related to green algae. It's photosynthetic. It's aquatic. Obviously, it reproduces with a tailed sperm because it's in water, because it can. So this is another division, liverworts. We've heard of them. We don't see them too often. They're not uncommon, but they're small. They're hard to see. They look these leafy ones look like a little smashed mass of green. It'll look like a little mass of algae at the edge of all those beautiful mountain streams. If you think of hiking up a trail and there's this mountain stream that's not flowing too fast and it's all full of green stuff coating the rock, if you pull it up and look at it with your hand lens, this is what you'll see. It's often a liverwort. Up here we have liverworts. 150. So there's 9,000 species on the planet. Somebody identified 150 species in the Methow. It was not me. But we've had, various botanical types in the valley still reproducing with a tailed gamete. So it got this name liverwort. Why? Because it has lobes that reminded our species, Homo sapiens, of a liver. Once we started dissecting human corpses and found out the liver is lobed and found out livers had lobes. And so the way the human mind works, it makes these mythological connections. And I wanted to dwell on that for a minute because it is the source of a lot of our troubles. This book was written called The Doctrine of Signatures in the 1300s, and it was pointing out that because God does not speak English, God's trying to speak to us in sign language, is desperately trying to let us know how to heal the things that are bad for us. So if you cut a carrot through the middle, it looks like an eye. So carrots are good for vision. Mushrooms look like an ear. This is God talking to us. And so fungi are good for hearing. Tomatoes and what? Tomatoes and the heart. And look at this. Obviously, walnuts have got to be good for the functioning of the brain. It's just bullshit, complete bullshit. There's a lot of bullshit going around. I don't know if you've noticed, but the really powerful point to me is the myth-making aspect of the human mind. We just make stuff up and we need to cut it out. I actually feel a little emotional saying that because of the larger issues burning on the planet right now. So this is a cartoon. And it's a very simple cartoon. And this is sort of a little evolutionary journey here. We could say this was maybe a proto-human, an Australopithecus genus that Homo sapiens arguably evolved from. It's just a cartoon creature. But we think we're at the end of the road, and we clearly are not. And it goes along with the myth-making power of the human mind. We're good at thinking. We're too good at thinking, and we can't discern reality from mythology. And fortunately, I'm not going to say any more about that. It's very meaningful to me right now. Hornworts. Well, it's a division. So how many hornworts have been found in Methow? None. I've never heard anybody. I've looked. I've never seen one. I didn't take that picture. Those aren't my fingers. It's off the web. And they're named because they're good for your horns. Well, that's just a joke. I don't know. I guess they look like horns, so they call them hornworts. By the way, I mentioned the word phyte, like coniferophyta, the conifers. The word phyta means plant. The word wort is Old English for plant. So hornworts means horn plant. Here we have bryophyta, that means moss plant. So this is one moss species we have in the Methow, and it's just to illustrate that we have this various mosses. There's 12,000 species on the planet, and I think it said 150 species when we had our little graphic up, our little chart. I took this picture in a hole, a watery hole in the Methow near my home here, because I dove in with a mask and snorkel and an underwater camera, and I found that this aquatic moss was growing on these rocks. And to prove it was underwater, I got a trout in the picture. And when I went to identify it, which you need a microscope for, this is what it was. It was Poseidon's. It's an aquatic moss, and it has this magnificent, intricate shape with a double leaf. All Poseidons have that double leaf, and that's how I knew it was Poseidon's. I mean, I'm not good at identifying mosses, but this one I could identify with a little help from my microscope. These are moss sporophytes, which means they're reproductive structures, but spores by definition only have one copy of DNA. So this is asexual reproduction. Plants do both, asexual and asexual. Mosses reproduce sexually. They have a male gamete with a tailed sperm that has to swim in water, which limits where land they can colonize. It has to be wet. Well, mosses get wet in the spring. I think of the mosses on our rocks around here, they're dripping with water as the snow melts. That's the sexual reproduction phase. This is the asexual reproductive phase. They make these microscopic spores that have a single copy of the DNA. They're created in these sporophytes, which have these ski caps on them to keep them warm in the spring, and the ski caps actually come off, and then the capsules have this lid that pops open, and then these teeth, which are folded inside the capsule, start, depending on the humidity, these teeth actually curve into the capsule and out. And as they curve in, they pick up the spores, and then when they come out, they cast the spores to the wind. And this is a microscopic picture of the intricacy of these organisms that are building themselves with no brain all over the planet. I mean, I think Tracy or somebody put a subheading in this program, the evolutionary of the flora of the Methow. It's a miracle. And I don't know, I don't think I said that because it is a miracle, but I don't like to say that because people think I'm getting religious on them. I like to call it miraculous. It's slightly less loaded. A lot of this stuff is incomprehensible, that living organisms know how to build themselves from a single seed or a single single-celled spore. These plants have all the information to live out their whole life. So another division, club mosses. I wonder where my watch is. Club mosses, another division of life. How many in the Methow? Not very many. 8. Well, this is a club moss here, right where I live. This shows you the quality of my soil. These are. Sorry, I don't know what it's doing. These are glacial cobbles. They're probably not unfamiliar to you if you're here in the Methow, but we don't have good soil in the Methow Valley. I have a garden, but I had to take rocks like this out of the garden, left by the glacier when the glacier melted 13,000 years ago, which is not very long ago, to get enough soil to grow plants. And this is not in the garden. But so this is a club moss. Club mosses have started to develop a vascular system. This is the first division of plants that has a vascular system. What does that mean? It means it has plumbing, it can grow upright. These don't grow upright. These are out there right now, right outside the door. It's a club moss. It only gets an inch high, but it's here. It is a club moss. This is actually a moss right here, I can see. But these are club mosses. This is probably a moss. But look at the rocks. They're covered with lichen. Lichens are living organisms that have their own life cycle. They are a symbiotic relationship between an algae, usually an algae, or a bacteria, a cyanobacteria, and a fungus. So these are symbiotic relationships, and they are able to make a living. How would you like to live on a rock all your life? Never move. But they don't mind. Club mosses. So we were talking about this is a club moss. This is a club moss. This picture in the lower right is a club moss, but it's a fossil, archaic club moss that existed 400 million, 350 million years ago. Oh, they used to be trees. They used to be trees 120 feet tall. They don't exist anymore. But the coal deposits from the Carboniferous period, which is 350 million years ago, are largely trees from club mosses and trees from horsetails. Horsetails used to be trees as well. Why are they called club mosses? Their reproductive structures look like clubs. And this is a photo micrograph of one of the
No, that's fine. I was kind
containers inside the sporophyte, just to show the intricacy that's going on here. We take these things for granted, but they're infinitely intricate.
We have a question, Dana. Ding, ding. We've got a question. How did the club moss get so tall without a vascular system? This is from Andy. How did they transmit water and nutrients to the top?
Andy, you troublemaker. Look at this, club mosses, vascular system. Club mosses are the first organisms to develop a vascular system.
Ah, so they did have
And
a
so,
vascular.
and so even now, I don't know if I have it in here. Nowadays, club mosses, I believe they don't get any taller than a foot. I have seen them at Roger Lake, where it's nice and wet. Roger Lake up on Tiffany, they grow about 8 inches tall. Why? Because they have a vascular system. They can move the water up that tall. I really should have my watch. You know, these computers have, oh, here it is.
Yeah, it's 9:48.
Time flies when you're having fun.
12.
Okay, we do need to speed up. So we're going, this is another division. It's the conifers. The scientific name is Coniferophyta, has another scientific name. So we've been reproducing with a tail gamete that has to swim through water. Conifers made the evolutionary leap of creating a male reproductive structure that could travel on the wind called pollen. Before that, plants, we talked earlier briefly that there were no plants on land. There have been plants on land for, I forget exactly how long, 300 million years. But that means for most of the history of the earth, there was no life on land, which is interesting to contemplate. But early life had evolved out of the water, could not retain water, could not colonize the uplands. Well, this is a journey to colonize the uplands. With pollen, you can reproduce anywhere. So these are male and female reproductive structures. This is a pine cone, but it's kind of a surprise, I think, that this is what pine cones look like when they first develop. It takes them almost a year to mature, and then they look like what we expect them to look like. The male pollen comes out of these male cones. This is a picture I took right here at home. This is pollen being cast to the wind on June 6th, 13 years ago. The air just fills up with pollen. It's not a very efficient way to reproduce. The pollen grain is so small, they can produce each tree can produce billions of them. It casts them all over the wind. It's very wasteful. It does work. Conifers cover a large portion of the Earth's land surface, but it's not very efficient. This is wasted pollen on Crater Lake. I didn't take that picture. Well, wind pollination works. So these are flowering plants. Alder is a flowering plant. Birch is a flowering. These are trees, obviously, but they are still wind pollinated. Not all flowering plants are pollinated by insects. Why? Because wind pollination works. Anything that works gets passed on. If you can successfully reproduce, it's a viable means of existing on the planet. I think so there are 300,000 species of flowering plants. 10% of them are wind pollinated. That's 30,000 species. So many things work. Well, what other options are there? These are armyworms eating an apple leaf. I actually took this picture at home. Well, once there were plants, how many insects were there on land before there were plants? There were none, because there was no food. Plants make all of the food on the planet through photosynthesis. We rarely appreciated point. You can't have animals before you have plants, because there's nothing. Animals started to colonize land. What did they do? They ate the plants. Well, then there's a chance for a symbiotic relationship. And I also actually seriously mean, even though it sounds a bit off topic, really you can see hope for humanity, because The drift overall is towards these symbiotic relationships. They didn't exist earlier. It was all competitive. There's a lot of symbiotic relationships now on the planet, and maybe humanity can move in that direction. So what is, in this case, what are we talking about? We're talking about the plants, the fact that first insects were eating plants and then moved into a symbiotic relationship where they started working with the plant to the benefit of both organisms. These are willow catkins. That's a wind pollinated design, but they put out a little bit of nectar at the base of every one of those little red dots. And so in the lower picture, if you go to willows in April in the Methow here on the valley floor, they sound like they're alive. They are buzzing with insects because willows produce a little bit of nectar to attract insects. So they are partially insect pollinated and partially wind pollinated. Why not? Let's try everything. A typical picture of a flower, just for a brief reminder with the various parts. So this is a classic flower, right? We recognize it: sepals, petals, male reproductive structures, the stamen, female reproductive structure of the pistil. Well, the interesting thing is there's 300,000 variations on this theme because there are that many species of flowering plants. No two species are alike. So all this variation, and they all work. So we talked about steer's head. It's a flower. It doesn't look like the classic flower, but it's a evolutionary experiment that worked, and they procreate and continue the genetic line. Different shapes for flowers. A fun thing about this is you can start to interpret why that flower shape evolved. I mean, there aren't that many choices, but you can start to evolve many things about the flower once you can start to read into the flower shape. So we know a lot of flowers are round like a wheel, they're radial. The thing about this shape is any insect can land there. There is nectar at the base of every petal, I will predict. I'm not sure what species that is, but any insect can land there and access the pollen. Well, will that insect go to the same species? There's no guarantee. If it's such a generalist, a lot of the pollen is going to be wasted because it's going to be carried to a different species, and chemically it will not work with a different species. You won't get a hybrid. You won't get anything. The pollen's just wasted. So many flowers have evolved this more complex design, bilateral design. It's harder to get to the pollen, hard to get to the nectar. Fewer insects. These are only pollinated by bumblebees. This calypso orchid, only bumblebees visit it. But bumblebees, as I said before, are very dependable pollinators. It will go to another calypso orchid and deliver the pollen. So it's just different strategies. Here's 4 of the 300,000 designs. And, we recognize these. Actually, I could not remember this one flower, so I couldn't label it. It has this weird nectary that goes right here. Anyhow, that's why I didn't label it. For buttercups, we know buttercups. If you pull a petal off a buttercup, it's got a nectary. You can see it with your bare eye right at the base of the petal. It's fun to see that. Kids love it. Where's the nectary in a columbine? It's way back at the end of this bract. So what can reach that nectar? Not many insects can reach that. You've got to have a tongue this long. Columbine's often pollinated by hummingbirds and probably moths and maybe butterflies. Monk's hood has a nectary up inside the hood. Here's the nectary taken out. There's a little dotted image of it here. Only an insect that can shove its way in through these petals and up into the hood. So it's a bilateral design. Only a few insects, again, probably bumblebees, are what pollinate it. By the way, bumblebees are known to just bite a hole right in the hood and cheat, because cheating exists in nature. Whatever works is acceptable. I circled the nectaries here. So the insects have co-evolved with the flowers, and insects have different capacities for reaching nectar at different distances. Flies don't have much of a tongue, and flies are not very good pollinators. Bees have a much longer tongue, up to a centimeter, I would say, half an inch. And then we know about butterflies and moths have long tongues, proboscises, to reach. This is coevolution. You don't need a tongue like that unless the nectar is put away. Well, I'm going to skip that darling little. There are various ways to pollinate flowers. These are shooting stars, actually up on, I forget the name of the hill, right near here. Anyhow, shooting stars are all over the place. So shooting stars were dodecathion. To my dismay, they changed the name to primula. Primula is a nice name. It means first, but dodecathion means 12 gods. And that's a fun name. And that's just because they grew on Mount Olympus, where the gods lived, and the gods loved them. Just mythological stories again, but not a destructive story like a lot of mythological stories. So look at the shape of a shooting star. Why they're called shooting stars? The petals are swept backwards. All the reproductive structures are forwards, and the petals are swept backwards. Well, they have this strategy to limit who can get at the pollen. The anthers only open through a hole like a salt shaker, and pollen will come out until you shake it at middle C, which is what, 700 vibrations per second? Well, bumblebees are able to vibrate their wing muscles at 700 vibrations per second, and the pollen shoots out of that hole and shoots all over the bumblebee, and it collects it and puts it in his little pollen baskets and carries it away and brings it to another shooting star and here's the female reproductive. I don't know how well you can see it, but it's sticking out in the middle there. And the belly, look at his belly, which is now covered with pollen, delivers that pollen. Coevolutionary relationship. This is alpine forget-me-not, which grows up at Hoodoo Pass only. The only place it grows in Methow is up at Hoodoo Pass. This is Snow de Glacier, which is also rare. Well, there aren't many in the alpine zone, and this is above tree line. This needs to find some way to not have the pollinators waste their time. So when these flowers are pollinated, the throat turns red. Hopefully you can see my cursor. I'm circling one that has a throat. Insects don't see red very well, and it will not bother coming to these flowers that have already been pollinated. Because it's cold up there, the pollinators can only fly on warm, sunny afternoons. We go up almost every year to look at these, and here's how you look at them. Here's the so this is an orchid that grows in Madagascar called Angraecum. And look at this is the nectary here. Look at how long that is. It's 9 inches long. Somebody sent this to Darwin, and he said, well, if it's got a nectary 9 inches long, there's got to be an insect that's got a proboscis 9 inches long to pollinate it. Otherwise, it wouldn't exist. And it was not found in his lifetime, but soon after, somebody found this xanthopan moth, and here's that 9-inch long proboscis. I put a little red line by it. It can stick it's co-evolutionary, a tight co-evolutionary relationship. I would say only this moth species can pollinate this flower, and that's fairly typical for orchids. They form very tight evolutionary relationships with one or a few species. If that insect species goes extinct, the flower will go extinct. So there's some danger to their evolutionary strategy, but it works. 34. Okay.
Dana,
1 minute.
yeah, great. This is amazing. Thanks for all these
We'll
stories.
We'll finish by 10:05, but you can obviously check out whenever you want. So this is time. Oops, sorry. Here's time. 400 million years ago down here in the bottom. 200 million years ago, there were no flowering plants. 200 million years ago, there were conifers, there were ferns. And an interesting thing about this is all these earlier evolved organisms still exist, and they exist in large numbers. There are only 600 species of conifers, but they cover almost half of the Earth's landmass. If you think of the northern latitudes, the northern boreal forest, it's all conifers. There's almost no flowering plant. In terms of numbers, this is not quite accurate. There are more flowering plants than this shows. I guess the numbers go up this way, but the flowering plants, in terms of numbers, I've mentioned several times, there are 300,000 species, only 600 species of conifers. But in terms of land coverage, they're fairly equal. Many things work. The evolutionary journey. I just covered April. I just turned a circle around April 8th here. This is when life first appeared on Earth. Not only is there no life on land for the first quarter of the history of the planet. Okay, so we're saying the history of the planet is a year, 12 months. So the first 3 months, there's no life. The first life appeared early in the 4th month. But for a quarter of the history, there was no life on Earth. Life appeared on photosynthesis didn't exist until July, till halfway through the history of the Earth. How can you have life if you don't have photosynthesis? Photosynthesis creates all the life, all the food on the planet by capturing the energy of the sun I've circled December 1st. These are the first land plants. And December 20th. It's a journey. Life is on a journey. It's not done. It's in movement. This can't see it fully. It got blocked out. Or I don't know if yours is blocked out. But I left the word out. The most important single metabolic innovation in the history of life on the planet. It's photosynthesis. This is the biomass of life on Earth. Most of the biomass of life on Earth. These gigatons are billions of tons, 450 billion tons of organic matter. Most of the life on Earth is plants. Why? They make all the food. How do they do that? They do it. Okay, I'm going to take the time briefly to, this is understandable. I warned you I was going to do this. So hydrogen atom has one proton and one electron. Sometimes it has a neutron, sometimes it doesn't. I don't know why, but it has one proton and one electron. That's a hydrogen. If it had two protons, it would be helium, but it doesn't. It has one. This is the electron shell. This is a model. It's not, I was reading in A Brief History. This is not really in any way accurate. It's just simplified so that our minds can grasp it. The atoms are this, but it works well enough. Electrons are in a shell, an electron shell around the proton. You know that. They're in an orbit. They're in a constant orbit. They're everywhere at once. That's the difficult part that we can't understand. Hydrogen has one electron. This is a true statement. Hydrogen has one electron. The electron shell holds two. Well, people talk about intelligent design, and we don't like it because they go right from there to the Bible. Well, that's an inappropriate leap. That's an inappropriate leap. But is this intelligent? These things are infinitely microscopic, but they have this design. Okay, so it holds two electrons, but it only has one. It wants another electron. Electrically, it wants to join with another atom so that it has its electron shell full. How does it do that? Well, one way to do that is two hydrogen atoms together. Hydrogen tends to form a molecule, H2. They share the electrons, the electron shell is full. You see, there is this intricate design of life at the infinitely minute level of the design of the universe. It doesn't mean that the Bible is true. It means it's incomprehensible. The electron holds true. So oxygen has 8 electrons. The first two goes in the first shell. Remember, the first shell holds 2. It's full. The second shell has the other 6, but the second shell holds 8 electrons. It's a rule of the universe. The second shell holds 8 electrons. Well, how are you going to fill that shell? Well, how about if you share 2 hydrogens joined with an oxygen, and you would have H2O. Have you ever heard of it? It's called water. Water is inevitable. Water will form because these electrons share carbon and oxygen to fill their electron shells. 2 oxygens combined with carbon. What does it form? Carbon dioxide. So this is a biochemist who knows what he's talking about. He's a Nobel Prize winner, Christian de Dove. There's no shortage of ordered self-assembly in the universe. That's the critical part, self-assembly. The universe is assembling itself. It's a natural extension of the orderly nature of atoms, actually. So he goes on to say that life, I love this phrase, life may be an obligatory manifestation of matter. All we needed was 4 billion years to make it happen. I don't know if you see what we're talking about here, but this tendency to complexify over time is built into the basic structure of the universe. It's really quite beautiful. And what level are we talking about? So atoms have, hydrogen atoms have this inevitable, profound structure. They have 1 electron and they want 2. You can fit 5 trillion hydrogen atoms on the head of a pin. It's ludicrous. It's just totally ludicrous. So photosynthesis. What is photosynthesis? Photosynthesis is breaking a water molecule apart. They're stuck together. They're electrically stuck together. Plants break the water molecule apart. They take this hydrogen right here and they plug it into the carbon dioxide, and you get sugar. This is the formula for sugar. And you get oxygen. The oxygen goes into the atmosphere. The sugar goes into the plant. That's why there's so many plants. We're speeding up here. It means this. So what are plants made out of? Plants are made out of carbon dioxide, which means what? It means the biosphere is appearing out of the atmosphere. I'm telling that we live on a very mystical planet. Brian Swim, who's a cosmologist, which is a scientific endeavor, cosmology, he says, well, that's impressive. The biosphere is appearing out of the atmosphere. So there is this film, very short YouTube, I recommend to you. I put it down here at the bottom. Google photosynthesis at MIT. And you'll see the 6-minute video of these graduates of MIT. And somebody hands him a seed. He's got a seed in his hand. And then they hand him this piece of wood. And they say, where does the wood come from? And this graduate at MIT, which is the most advanced engineering institute on the planet, he says it comes from dirt. He says, well, I guess plants come from dirt. He's wrong. He doesn't know. Nobody understands photosynthesis. You need to watch that. Photosynthesis at MIT. Also, photosynthesis pumped, the atmosphere is 21% oxygen. Here's this line, is 21%. It has gone up to 35%. Fortunately for us, it's not that anymore. It's now 21%. That oxygen is for breaking apart that sugar that plants made. We breathe in, why do we breathe oxygen? We breathe it to break apart the hydrocarbons made by photosynthesis and release the energy of the sun in our bodies. It does other things. We're going to skip that. We're going to skip leaves, except that they exist. And there's so many varieties and they have a purpose. So here's a bunch of flowers. I was driving along. I like to say, I go on for vacation. I go to war zones because the hotel rooms are really cheap. So I went to Afghanistan and we were driving along this little minibus and there were all these flowers. I said, stop the bus. I said that literally. I said, stop the bus. And I got out and I took a picture of these crocuses. And the point really is that there's all of this struggling on the planet. Afghanistan is a tortured country. The flowers still bloom there. Natural processes are still taking place there. This is actually a wheat field in Afghanistan. And we went to this village we were on our way to a village called Istalif. This is a child in Istalif. And it just touches me that humanity is so beautiful. This is a young girl up on a hill in Kabul. I'm going to skip that. So the rooms were cheap in Palestine. So I went there and I found this cyclamen that we grow as a houseplant growing wild in Palestine. This is a little Palestinian girl. She's actually famous. Her name's Jana Tamimi. But I brought a hand lens for her and a book on the wildflowers. So maybe the beauty of the world can save us from like a human travail. Can't summarize that anymore. This is about the last slide. Emergent qualities of plants. I like that word emergent. The biosphere has emerged in an evolutionary sense. It didn't used to exist. All of the uncountable species on the planet did not used to exist. Plants are the primary source of biomass. Biomass captures the energy of the sun. Without biomass, plants change the chemistry of the atmosphere. The atmosphere is 21% oxygen. Oxygen is very reactive. Why is it atmosphere 21% oxygen? Because of plants, because of photosynthesis. Plants are a geologic force. They have sequestered billions of tons of carbon, all that coal. And we didn't talk about this, but the iron deposits are because of photosynthesis, because of the oxygen in the atmosphere, then reacted with iron, and the iron precipitated out. Plants make terrestrial life possible. They also make life in aquatic life possible. I don't know why I put that. They're the source of fossil fuels. I mean, I have wood burning in the stove over there. I have propane heat. It's all plants that got fossilized. The energy of the sun contained in hydrocarbon bonds of plants. We evolved in trees. What are trees? They're plants. Last one, fire. It's hypothesized. Maybe you know what's the book, Catching Fire. I recommend the book called Catching Fire. When you cook food, it doubles the amount of nutrients available for food. Well, the human brain uses like what? 1/3 of the energy that we take in through eating is used by the brain. Why is that much energy available? Because plants cook our food for us. So Teilhard de Chardin, you probably remember his name. I'd like to go back and read some of his stuff. But he's a poet. He's an anthropologist and a Catholic priest and a poet. What's the purpose of evolution? Ever more perfect eyes in a world in which there's ever more to see. These are pollen grains. This is the beauty of the world on a microscopic level. The beauty never ends. It goes in all directions. So if you want to go on an adventure, you need to throw some bread and tea in an old sack and just get out there in the world. Good organizations. This was sponsored by Methow at Home. Great organization to participate in, community. I gave this slideshow for Okanagan Highland Alliance, another good group, Methow Natives, and the Methow Naturalist. If you don't subscribe, you should. Here's the first Methow Naturalist, March 1996, and here's the most recent Methow Naturalist, number 111. And that is the end. Well, I went over time. Sorry.
Oh, that was great. All sorts of interesting, fascinating, beautiful stories in there. Thank you so much, Dana. And thanks to everybody coming. I'm going to go ahead and end the recording right now.